pressure membrane process. Thank you.
Okay, thank you. Thank you for the nice introduction. And first, I also would like to thank Professor He for organizing this great seminar, so we can have this platform to share our recent progress on this emerging contaminants removal. So today I'm going to talk about some study I have conducted in the past a few years, so which is on this self-assembly assisted removal of emerging contaminants by low pressure ultrafiltration processes. So basically, we all know this kind of like emerging contaminants, which is like highly hazardous, and they are also associated with this high health risk. And another thing is most of them are very quite environmental persistent. So that means they cannot be degraded very fast in the natural environment. So that's a problem. And the major challenge of this emerging contaminants is that the existing water treatment technologies is ineffective in control these emerging contaminants because of most of the process involves a high chemical input, and also some processes like has a high operating cost, and also, for example, the selectivity of this process is relatively low. For example, if you have this advanced oxidation process to degrade the pollutant, some of the pollutants cannot be degraded, or they can be degraded in the meantime. So basically, membrane technology has emerged as an effective control of the emerging contaminants over the last decades. So we are all very familiar with membrane technology, because if we differentiate those processes using their size, basically we can classify membrane processes from microfiltration to ultra to NF to RO based on their size. So in terms of the emerging contaminants, generally they have a size around like 1 nanometers. So basically what we do is that we use this nanofiltration or RO to reject these emerging contaminants, which is quite effective. But the thing is that they still have some advantages. So because today in this room, I think we have a lot of people doing RO and NF. I'm not going to talk about a lot of disadvantages. I just want to show another avenue, which shows that maybe we can think about some other processes to remove these emerging contaminants. So the thing is that I'm thinking either we can move from this high pressure process like RO or NF to like low pressure processes. So what we do is that generally what we do is that we want to make the pores smaller. So basically we just treat the pores smaller, which can effectively reject the contaminants. But the idea is that whether we can do another thing is that we can make the contaminants greater. So in this case, we can use some pores with larger size to remove these emerging contaminants. So actually, I call this process MCG. Okay, so this process actually is not new process, because if you think about our conventional membrane process, it does the same thing. Because, for example, in coagulation or flocculation, we also add the coagulant or flocculant into the system. So basically, after some mixing or some process, so this colloidal phase will be removed. So most of this phase is made of the large molecules or nanoparticles with a size range like 1 nanometers to 1 micrometers. So now what we want to do is that we want to switch this membrane technologies from this high pressure system to this low pressure system. So in this case, we are able to remove these emerging contaminants because most of them are small molecules with a size smaller than 1 nanometers. And in this process, I add an A here. So if you can see here, did anyone could tell me what this A stands for? So if you read this title, this A actually stands for making contaminants greater again. So I guess most of you are very familiar with, because Donald Trump is currently is of the hot topic, right? So what we do is also to make this mega, okay. So today I'm going to introduce two self-assembly systems. So the first one is this self-assembled nanoparticles, and the second one is this self-assembled micelles. So I will start with the first one, which is on the left. So this work actually was done by my former postdoc, Dr. Su Xu. So currently, she is a faculty member in South China Normal University in Guangzhou. So let's start this first journey. So what we do is that we firstly synthesize these nanomaterials using these enzymes mixed with the monomers of the nanoparticles of the ZIF8. So basically, during this synthesis process, the enzyme will be encapsulated inside the nanoparticles. So what enzyme do is that the catalyst will basically to decompose the hydrogen peroxide into oxygen bubbles. So basically, these nanoparticles can move around in the solution phase. And another thing that for the HRP, because we all know that HRP can decompose the hydrogen peroxide, and so it will transfer electrons. So in this case, we are able to decompose the phenolic compounds into other chemicals. So after the synthesis, we first verify their presence inside the pores, inside the particles using this fluorescence technique. So we can see that two enzymes, both HRP and CAT catalysts, they are evenly distributed in the particles. And so this is a good sign. And after that, we also do some material characterization using XRD, FTIR, and BET. So basically to evaluate how this enzyme will affect the like crystalline structure and also like pore size of these nanoparticles. So the good thing is that, for example, for enzyme regarding their crystalline structure in XRD, so basically the presence of enzyme will not affect this kind of crystalline structure of the ZIF materials. And in FTIR, we just use it as evidence to confirm that actually this enzyme is encapsulated within the nanoparticles. Regarding the BET, basically shows that after the encapsulation, so the pore size of this ZIF nanomaterial does not change a lot. So all of them are like showing some good evidence of this enzyme encapsulated nanoparticles. So next thing we want to do is that we'll demonstrate this idea using this UF system. So what we have that if we have this UF system with a pore size of 15 nanometers, and we also have the phenolic compounds. We all know that this phenolic compound is like very, very small, like molecular weight less than 100, right? So basically, if you do not have anything, so basically the UF system cannot reject these molecules. And so this is our result. As we expected, for the UF alone, here, these purple columns, we can see that for all these phenolic compounds, rejection is relatively low. But whereas if we add the nanomaterials without enzyme into the system, there is some enhancement of the rejection compared to the UF system, which is basically because of this adsorption effect. And after that, if we have this ZIF plus the enzyme plus the UF, this system actually gave us a much better rejection, because for most of the compounds, we can achieve like 100% like rejection. So generally, we firstly demonstrate this idea, actually it works. So the next thing is that we also evaluate some other phenolic compounds in this system. So basically, we selected a range of phenolic compounds in the wastewater. So what we achieve is that we can see that for some of the contaminants, they can be rejected effectively, whereas for some contaminants, actually their rejection is not that excellent. So this is largely because of their hydrophobicity of these molecules. Because if we plotted their X log P value along this axis, we can see that for the molecules which can be effectively rejected are largely the molecules which has a higher X log P values. So this is because these molecules is highly hydrophobic. So they tend to adsorb on the nanomaterials once they degrade on the surface. So next thing I want to show is that this system actually is pretty stable. Even in the presence of that NOM, we can see that we can still achieve very high rejection. And another thing that, so because during our preparation, we know that the metal ions, for example, especially some heavy metals, they are detrimental to the enzymes. So we also demonstrate that when with the presence of the metal ions, if you encapsulate it inside the nanoparticles, they can still return their performance. Whereas for the free enzyme, actually they quickly lose their performance. And also we also evaluate the temperature effect, because for temperature effect, we can see that if you have this encapsulation, which will also enhance its stability within the nanomaterials. So this is generally shows that actually these nanomaterials provide a shielding effect for this enzyme catalytic reaction. So next thing we want to see that is this like TM image after the reaction. We can see that this is the age of the nanomaterials, which has this like hexagonal shape. Whereas on the surface of this material, we can clearly see a lot of like fluffy and soft materials or soft on the surface. So basically, we watch this products out of the material and determine their composition using the LC mass chromatography. So what we observe is that actually those products are generally made of the oligomers. So basically, we can detect the tetramers, pentamers, or like a range of the oligomers on the surface. So now we can review their mechanism. Is that basically what happens is that for this phenolic compound, basically they contact with the enzyme, and then they come out of the nanomaterials and to polymerize or form this coupling reaction to form this like very fluffy material on the surface of this nanomaterials, because you can see that this nanomaterial is quite large compared to the pore size of UF membrane. In this case, that's the reason they can be effectively rejected by our system. Okay, and after finishing the first one, let's switch the gears and move on to the second one, which is a safe or simple micelles. So this work was conducted by my master students, Ms. Zheng Zhen. So generally what we do is that we mix this emerging contaminants PFOA with a surfactant. So first, let's see their interactions. We want to evaluate how the PFOA actually interact with our surfactant. So basically, we conduct this QCMD experiment. We can see that for PFOA, actually, it does not absorb on the surface of the gold sensors, which is also the reason that PFOA cannot be effectively rejected through like adsorption process. Whereas if we have like at the system with the CTAB, we can see that CTAB actually can effectively absorb on the gold sensors. If we further rinse the system with the PFOA, we can see that actually PFOA can drag some CTAB out of the surface of the gold centers. So this is the first evidence that demonstrates PFOA actually has a strong interaction with the CTAB. So next thing we want to show is that basically we use DLS to determine the size of our micelles in the system. So basically we can see that for CTAB, it has a micelles around like 50 nanometers. Whereas if we have this composite, the micelles can be even larger with a size of like 100 nanometers. And also we determine the critical micelle concentration in our system. We can see that with the presence of the PFOA, its CMC actually decreased a little bit compared to the system only with CTAB. So this is indication that actually PFOA molecules involved in the micelles formation during this in our system. So next thing we want to evaluate their rejection. We also select a membrane. So this time we use an even larger size membranes, which has a size of like 40 nanometers. So in this case, we can what we expect is that actually PFOA still cannot be effectively rejected. There is some rejection. I largely attribute it to some like adsorption effect. So if we further add the system with the CTAB, what we achieve is that like 100% rejection. So this is an indication that actually they form this large aggregates in the solution. So that's the reason they can be effectively rejected. So also, maybe some of you will argue that is there a way that we can decrease the CTAB use? So we also evaluate the effect of CTAB concentration. Basically, we decrease the CTAB concentration. So in this case, we can still achieve like pretty like near complete rejection of the PFOA molecules. And so this is the reason we attribute it to the presence of the concentration polarization effect. I guess most of the membrane experts are very familiar with this process. So what we do is that because we have this stir cell in our system, we do some mass transport analysis. So in this case, this analysis will enable us to look at the surface, the concentration of the CTAB near the surface of the membrane, and also we visualize the concentration of the CTAB concentration on the membrane surface through this like concentration mapping files. So we can see that even with a low concentration of the CTAB in a box solution, actually on the membrane surface, actually its concentration is much larger than you expected. In this case, they can still form some aggregates or pre-micelles or even micelles. In this case, that's the reason we achieve like near complete rejection of PFOA just using the low pressure UF membrane system. So after that, we also do some like further evaluation on the carbon chain effect. So what we have is that we use a range of the PFOA molecules. So we can see that for the PFOA molecules with the carbon chains with the numbers larger than 5, we can achieve like near complete rejection. If we further decrease the carbon chain to 3 or even use some like new PFOA molecules, actually the rejection is not that expected. So this shows that actually the effective removal of PFOA in our system is largely determined by these long carbon chains. So next thing we want to evaluate is this chain group and also the charge effect. Basically, we use this molecule with the same carbon chain structure, just without the fluorinated atom on its carbon chain. We can see that this CTAB system does not work in this system. Whereas for other systems with PFOA, we can achieve like near complete rejection. This shows that actually the hydrophobic interaction between the CTAB and the PFOA molecules actually play a major role in forming this micelle, which determines their following rejection by the UF membrane. Actually, I also have other data which shows that actually this electrostatic interaction also plays some minor roles here. So this is our mechanism we propose for this micelle-assisted PFOA rejection. Basically, if we don't have any CTAB or any micelle formation, basically the PFOA will easily penetrate from our UF membrane. Yeah. So if we have this CTAB micelles, which can form this more large size micelles in the system. So in this case, which will enhance their rejection by the low pressure system. So here are some like take-home messages. Basically, in today's talk, I showed two cases of this like self-assembled systems, which combined with the UF large molecule UF large pore size UF system to effectively reject the small molecules using our system. So basically, we can see that this kind of like system has several advantages. So compared to some normal membrane technologies. So with that, I would like to acknowledge my thanks to my founding agencies and also my colleagues at the National Synchrotron Radiation Facilities, both in Hefei and Shanghai, and also my colleagues in the Department of Environmental Science and Technologies in USTC. And more importantly, I would like to thank my postdocs and students at the MET lab, which stands for Membrane Engineering and Environmental Technologies Lab. Okay, so with that, I would like to thank for your attention. I'm happy to take any questions.
Thank you. So we will welcome